Today's presentation is going to be all about the anchor bolt pullout features that are within RISABase. So to begin with, I'd just like to point out that the version that we're going to be using here today is version 2.0.3. That's the latest RISABase. Now, some of you may already own version 2.0, but I definitely recommend taking a look to see if you're running this latest one. We have added some additional enhancements since version 2.0 came out, and we will be covering those in today's presentation. So today's presentation, we're going to be talking about four main topics here. First, we're going to give you an overview of RISABase. We're going to talk about the various anchor bolt failure modes that are in part of the ACI Appendix D. We're going to be taking a look at seismic considerations, and we're going to be looking at interpreting the results. So to begin with, let's talk about RISABase. The first version of RISABase was released in 1998, so it's been around for a while. And when it first came out, it was strictly a baseplate design software. Some ideas were put forth for anchor bolt pullout, but the problem was that in 98, there were various building codes all across the country and no standardized way to design anchors. Now, one interesting thing about RISABase that really sets it apart is that it's a finite element analysis-based program, and it's doing full biaxial analysis and optimization. So it really goes a step beyond the basic hand calc methods that you get out of the aisc, which are going to assume rigid plate behavior. Now, another great thing about RISABase is that it allows the placement of custom anchor bolts. So you can either have your anchor bolts located through some various templates, or you can put them in at any XZ coordinate within the system. And that's especially great if you have a misplaced anchor bolt in the field, as if that were to ever happen. You'll be able to address that situation with the program and see how your base plate stresses are going to be affected. So let's take a look at the anchor bolt failure modes. As of the IBC, we now have the ACI 318 Appendix D referenced for all anchor bolt pullout checks. And in this case, we're using the 2005 edition, and that is referenced per the IBC 2006. And in Appendix D, you have 7 failure modes. And you also have to take a look at individual versus group failure of anchors. Now, these 7 failure modes, granted, most of them are not very common. In fact, when you take a look at the simplified methods from the older building codes, the common failures really fall in that range. But ACI did recognize certain uncommon failure modes that weren't really being addressed in the past before. And of course, taking a look at the individual versus group failure, you can have a lot of difference between those. Now, for anyone who's done any Appendix D hand calculations, you know that they're very complex, very tedious, and generally you want to avoid them. And that's one of the reasons why we implemented it into RISABase, is because we recognize the value in having a program that can do that for you. So let's talk about the different failure modes that you can get with anchors. Well, the first is going to be anchor bolt steel, and this is actually a controversial topic because AISC generally would govern steel strength, but ACI actually references it here. In order to avoid any sort of problems in terms of our program implementation, we're going to check your anchor bolts for both the AISC requirements and the ACI requirements and report them both back to you. And we leave it up to you as to which one you consider governs, although for my own designs, I prefer to just meet both requirements. Now, concrete breakout in terms of cone failure is another tensile failure. Anchor bolt pullout is another one, and side face blowout is another one, although typically the first two are going to govern. Now, there's 3 shear failure modes. You have your anchor bolt steel failure, which is just a shear failure of the anchor bolt. You have the concrete cone breakout, and that's a sideways cone breakout in your pedestal, and then anchor bolt pry out, which is another less common failure mode. So let's take a look at these. I've got some illustrations on screen here to show you what these different failure modes look like. So anchor bolt steel, this is going to be a rather typical one that you can understand. As the base plate begins to pry up on the bolt or just lift on the bolt, you can get a straight tensile split through the bolt there. And this can be due to prying action as well, which I should mention that RISABase does account for because it's capable of doing the flexible plate assumption. Now, concrete breakout is where you get a cone or pyramid breakout out of the concrete, and this is where the head of the bolt is going to bring a considerable amount of concrete along with it. And this is a very common failure mode for both individual and groups, especially when you have anchor bolts close enough together to where the pyramids actually intersect each other. Now, anchor bolt pullout is more common for your post-installed anchors, but what you have here in this case is a localized failure right around the head of the bolt, and the bolt's actually just pulling out vertically, maybe causing a bit of spalling at the surface. But it's different from the cone breakout because it's engaging significantly less shear area on the concrete. Side face blowout is a failure mode that only really occurs when you have anchor bolts that are very near the edge. And so what you can see here is that localized stresses from the head of the anchor aren't able to develop in the concrete, and they actually shoot right out to the edge of the concrete and blow out the side there. And that can actually cause the whole portion of the concrete above that to experience failure. So it's not a very common one, but for very close to edge embedments, it is something that you definitely need to consider. Now for the shear failures, we've got the anchor bolt steel failing in shear once again, and we've got an illustration of this, and this is also going to cause some localized concrete spalling here. We have concrete breakout, and what this is similar to the tension cone breakout, but in this case we've got shear that's pushing at the bolt plate interface into the concrete, and what you're getting is a sideways cone breaking out of the concrete. And once again, this is something that only happens when your anchors are relatively near an edge. Now, when your anchors are inbound much more, say in the middle of a slab, you're going to get something more like this, more likely, which is the anchor bolt pry-out. And in this case, the anchor bolt is actually capable of rotating because a slip plane forms when you get a shear rupture in the concrete, and that triangle of concrete you see on the left is able to pretty much push itself up and out, and the bolt's able to almost flip over on itself. And so that's another failure mode that is definitely something to consider. And one of the nice things is that RISABase automatically is going to check all these failure modes for you. Regardless of whether or not they govern, will determine whether they govern and will determine what the capacity is for each one of these modes. So let's take a look at one other thing, and that is group failure. You not only have to consider the individual anchors, but you have to consider how all the anchors are going to be acting together in a system. Now what you can see here are some diagrams that were taken right out of the program, and you can see that red cross-hatching. That represents an actual shear breakaway, and that's that shear cone breakout failure that we mentioned earlier. And you can see that there's various methods you can go about. So the failure and the load could occur in the same direction, but you can actually have a situation where your load is heading in this direction and your failure is going in that direction. And that's just a situation where if you're close enough to the edge, those anchors can actually break out sideways in cone failure. It's not very common, but it's something to consider. And when you consider more than just 4 anchor bolts, all the various types of combinations you can have between these and the various group failures, you quickly end up with a very large number of failures that you have to analyze. And as a result, you're going to see there's actually a very large amount of data that's output from the program when you're taking a look at these different failure modes. Now let's talk about the seismic considerations that are made within the program. We're taking these straight out of the ACI Appendix D. Now one of the things in the 2005 edition is that they refer to having a 25% strength reduction for all of your calculated capacities whenever you're in what they refer to as a high seismic zone. And in the 2008, they've actually gone forward and sort of clarified that, and I believe it's seismic design category C, but you can always check in the book as to whether or not this is a governing situation. So we have controls in the program to be able to set this strength reduction and have it automatically apply to the seismic load combinations. Now another thing to consider is that seismic failures with embedded anchor bolts must be ductile. And so what you need to have here is either a failure of the column prior to the anchor bolts failing, or you need to have it in such a way that there's going to be a steel yielding that occurs during an earthquake as opposed to a cone of concrete breaking out. Obviously, we want to avoid those sudden rupture failures in concrete, and we'd rather have a seismic failure, which is much safer, a ductile failure, that is. And so, of course, in the ductile failure, the steel yields first, and so what you're going to look at is what sort of elements are going to be able to control for that. Now, in this case, we're considering the embedment of the anchor bolts, and so it's the anchor bolt itself can either yield in elongation or in shear, or you can actually add some supplemental reinforcement that's prescribed by the code, and that can pretty much pick up the slack after you've already had some sort of yielding, and it can hold that chunk of concrete together that's attached to your anchors. So that's something very important to consider. So at this point, let's take a look at an example within the program. What we're going to look at here is a pretty typical setup, a W14 by 99 column. It's going to be placed on a 3-foot by 3-foot pedestal. We're going to apply dead, live, and earthquake loads to this. In this case, we're just going to do some uniaxial bending to make the results a little more clear, although definitely you can take a look at biaxial bending with this as well. So now I'm going to switch over to be within RISABase. Now, some of you may already be familiar with the program here, and we're going to be going through first the input on this and then spending a lot of time on analyzing the results that come out of it. But to begin with, for those of you who aren't familiar with the input in the program, with RISABase version 2, we have a data entry toolbar, very similar to RISA 3D and some of the other products, and we've set the program up such that all you need to do is walk through these dialogues one at a time, and as long as you address everything in each dialogue, then you'll be ready to solve and ready to go. So let's take a look at some of the options here, because there's quite a few options, and it can definitely be overwhelming when you first launch the program. But once you become familiar with it, it's all just second nature. So, as I mentioned, it is a finite element analysis program. So we're going to take the base plate, and we're going to submesh it into a bunch of small plate elements that are connected to each other. We're going to place those on top of a whole series of compression-only springs. That's what represents basically the grout or the concrete that's on the underside of the base plate. Now, when we create that mesh, we can create a coarse or a fine mesh. Now, the fine mesh is going to give more accurate results, but it can take a little bit of time to solve. There's other ways around getting around that solution time, but for now, I do want to use a fine mesh solution for this example, so we're going to go ahead with that. Now, for the base plate and anchor bolt, we have several different design codes. You can see the ASD 9th and LRFD 2nd. Those are left over from RISABase 1. Of course, now in RISABase 2, we have the 13th edition in here. And so I'm going to check this one using the 13th LRFD. Now, one of the reasons why I like to go with the LRFD is because concrete, as you know, is an LRFD design as well. And so by going with that, typically I can use just one set of load combinations as opposed to having to generate two sets of load combinations. But either way, you're going to get the 13th edition results no matter which method you choose. So under model description here, I'm not going to bother filling any of this in, but when you print reports out of the program, this can automatically populate all the header and footer information in your reports so that when you file this stuff away, you can figure out later on what you were actually working on. So as I mentioned, we sort of go down the list here. So from global parameters, now that I'm done with that, I'm just going to close that window, and I'm going to go into the next one, units. Now here I can choose any various different number of units. In this case, I'm just going to use the standard imperial ones, and so I'm going to hit OK. You can go with metric as well. And from there, now I'm going to come down to the next dialog, which is column shape. So I'll click on that. So you can see we're just sort of moving down here. Under column shape, we have all of the different databases that are also available in RISA 2D and RISA 3D, all the foreign ones. In this case, I'm going to use the standard aisc database. And for the shape, I'm going to go ahead and choose a W14 by 99. Now you can see I could have also chosen a pipe or a tube as opposed to a wide flange, and pipe does also include round HSS. Now I can choose how my connection is going to be, and this is just going to determine how the column actually connects to that finite element mesh. Are we going to be able to get tension and shear transferred on just the flanges or on the web? In this case, I would say that it's going to be welded all around, so we're going to just specify welding on both the flanges and on the web. The next dialog that we enter is the base plate dialog. And in here, we get this nice chart, the legend in the upper left corner, that shows you what all these different dimensions correspond to. And so let's sort of go through here and set how we want this base plate to be done. So for the yield stress, I'm going to just go with a standard A36 on here. So it's going to be 36 KSI, and we have the 29,000 KSI modulus of elasticity, very typical. For the column eccentricity, I can set the column eccentric to the center of the base plate, and that's a great tool to use. In this place, we're going to take a look at a little more simplified setup, and so we don't want to set any of these more advanced things yet because we want to take a look at the results in a simplified way to begin with. Now, I can also set minimum column to edge distance because the program's actually going to optimize my base plate size for me, but I want to make sure to leave enough room for field tolerances and for fillet welds around it and the such. So I'm going to leave 1 inch surround on that column. Under the base plate design parameters, I can specify maximum and minimum lengths. And so we had mentioned earlier that my pedestal was going to be 3 foot by 3 foot. I'm going to give this a max and min length and width of 30 inches and a minimum of 24. Now the plan increment is how we control how we optimize the size of this base plate. And so right now that's set at 1 inch, and what that means is the program's initially going to try out a 24 inch by 24 inch base plate, which are both my minimums, and then it's going to step those up in 1 inch increments separately. But I don't want to end up with an odd size base plate here, so in order to get something a little more normal, I'm going to set a plan increment of 2, such that the dimensions only end up being even. Now I can also set a max and min thickness. In this case, I'll allow it to go all the way up to a 2.5 inch base plate. And I'll set a minimum at 0.75 because any base plate that comes out of here, I don't want it to be banged around while it's actually being shipped. Now furthermore, I can set a thickness increment of 1/4 inch so that we don't end up with any odd dimensions. And lastly, in order to cut down on any mistakes that could happen during the fabrication process, I'm going to set this up as a square base plate, which I can click here. Now this next option, force base plate to be rigid, this ties back to the whole AISC hand calc method. In the AISC, what they assume is that your plate is infinitely rigid out of plane to itself. So therefore, it's completely incapable of bending locally anywhere. Instead, you just have an overall bending moment and a solid plate that sort of tips up as you apply moment to it. Now, for hand calc methods, this is great, but it's not exactly very realistic, and it can end up giving you some very conservative results sometimes and some very unconservative results sometimes. We give you the option to solve rigid or flexible in the program, whatever your preference is. One of the nice advantages to solving flexible, though, is that we are going to account for the prying action that's occurring on your anchors when you have them near the edge on the base plate. And that is a sort of significant force to consider because that can actually increase the tension force in the anchor, even though you have no net increase of force applied to the overall base plate itself. So for now, we're going to go with the standard flexible solution on here. Now the pedestal parameters, this is where I enter this in, the 36 inches, and this is going to determine what the edge distances are for the anchors after we solve, so that when we consider those localized edge failures we looked at, such as the side face blowout and the side face breakout, the program will know how much distance it has between the anchors and the edge. And then for height, there are also considerations in terms of the side face breakout and shear. When you have that cone failure, it's actually occurring in 3 dimensions, and so if your pedestal is short enough, that can actually impact the shape of the cone that breaks out of it. In this case, we're just going to go with a 36-inch height as well. I'm going to use standard 4 KSI concrete, and this is not only going to set what the allowable strength is of the concrete in terms of the anchor bolts and in terms of the concrete bearing itself, but this is also going to control the stiffness of the pedestal. I mentioned earlier that the finite element analysis uses those compression-only springs, and we actually calculate an E value based off of this F'(C) to know how stiff the springs need to be. And I'm going to use the AISC provisions in order to determine what is essentially an allowable bearing stress on that concrete due to the base plate. Because anchors aside, we want to make sure that we don't have any failures just due to base plate compression either. So So the next dialog we're going to go into, moving along the data entry here, is connection. And in here, this is where I can specify whether I have a plain base plate or whether I have it stiffened using either welded stiffeners, clip angles, or channels. And in this case, we're just going to go with a plain setup. Now under anchor bolt layout, you can see we can actually do a setup with no anchor bolts at all, so we could check that situation. And we can do one with just a anchor bolt on each side of the web, but neither of these are very common. Instead, we're going to go with what is the most common, which is the flange side layout. And here I can set up anchor bolts in a number of rows, and I can put a number of bolts per row on each side of the flange here. Now, another option we have, as I mentioned earlier, is custom. And so you can see if you had a misplaced anchor rod, you can put that on there. One of the downsides to custom, though, that you should be aware of is that we can't do any group failure calculations for the anchor bolts. And the reason for that is because all of the guidelines in Appendix D that relate to group failure all refer to sort of an evenly spaced grid of anchor bolts, and they don't really reference how to calculate the overall failure cone for a tension pullout, for example, when you've got a situation like you see in the image here. So instead, we're only going to give you individual failure results, and we leave it up to you to determine whatever method you feel is prudent in order to take a look at the group failure. So as I said, we're going to go with the flange side here, and I'm just going to do 2 bolts per row and 1 row per side. And what that really means is I'm just going to have 4 bolts on this plate, and they're going to be at each corner. So I'll close out of here, and next I'm going to come into the anchor bolts dialog. The anchor bolts dialog, we once again give you a legend up at the top so that you can tell what all these various input options are. And this is where the most of the input options are, is in this anchor bolts dialog. So let's take a look. For anchor bolt size, in this example, we're going to go with an 1.5" diameter anchor bolt. Now for projected length, if you take a look in this image up here, we show you the projected length as being from the top of the concrete to the top of the anchor rod. Well, that seems like a pretty meaningless dimension. And to some degree, it really is. Whenever I'm entering this, I prefer to do top of the concrete to about the middle of the nut on the anchor rod. Now, what does this actually affect? Well, as I mentioned, we're doing that FEA solution, and we have the compression-only springs that represent the concrete underneath the plate, but we also have two-way springs that represent each anchor bolt, because you have to consider that even though the plate is held down by anchor bolts, those anchor bolts do have some stiffness, basically, in terms of their longitudinal stiffness. So they can stretch out somewhat when you apply some load to them, and when they stretch a bit, that can actually redistribute the loads in the anchor bolts. So you need to definitely consider how that's going to be happening. So for projected anchor bolt length in this example, I'm going to use 6 inches, and this is going to control how tightly that plate is clamped down to the concrete wherever there's an anchor bolt. Now we have minimum anchor bolt to anchor bolt spacing. In my case, I'm just going to have 4, 1 at each corner, so I won't really have to worry about that. I don't have any stiffeners, so the anchor bolt to stiffener spacing won't make any difference. The anchor bolt row spacing, I only have 1 row per side, so that's going to be irrelevant for this. And I have an anchor bolt to edge spacing. Well, that is something that I care about, so I'd like the program to size this base plate with an 1.5" edge distance for all the anchor bolts. Now down here we can specify whether or not there's going to be shear lugs in this model. And the shear lug is going to take all the shear from the column and put it directly into the concrete rather than putting it through the anchor bolts or the base plate. So what this will effectively do is allow us to do a tension-only check for those anchor bolts and just dump the shear right out of it in terms of the checking. So we're not going to put that on there because we do want to take a look at some of the combined shear and tension effects on the anchor bolts. Under anchor bolt design here, I can specify check anchor bolt size. And when I check that box here, we've got the anchor material. Now, this particular dialog box is controlling the aisc anchor bolt design checks. And so for here, we're going to go with the typical, the F1554 to 36 KSI anchor bolts. And that's just your standard anchor bolt right there. When I have threads excluded, that relates to the N versus X, basically, in terms of bolt design. And we are not going to exclude the threads from the shear plane in this example. Now, I can also put in user-defined values for the FY and the FU of the anchor bolt. but in this case, I just want to use the standardized values of the F1554. Now, under anchor bolt pullout capacity, I'm going to check this. So this checkbox determines the aisc checks for the anchor bolts. This one determines the ACI checks for the anchor bolts. And so here's where we can specify what type of head we have on the anchor bolt. We can specify what sort of concrete it's embedded in. We can take a look at the total anchor bolt length. Now, the Appendix D always refers to your effective embedment, but right here we're taking a look at total length. And if you take a look at this image up here, the total length minus the projected length is what your effective embedment length is. And so in this case, I've got 16 inches and 6 inches, so I would end up with 10 inches of effective embedment. And that's not quite enough for what I want for this example, so I'm actually going to bump that up to 18 inches. And I'm going to specify a hex head bolt. Now the seismic modification factor, I mentioned that one earlier as to how that affects things, and so we're going to leave that 25% in because we're going to assume that we are in a higher seismic design category for this example. So now down here we have some additional settings. Built-up grout pad. I'm going to assume that this base plate is bearing right on the concrete. Now we have cracked concrete, and I can check that box, but oftentimes when I'm going through these, I am curious to know, how does this actually affect the design? Why does it matter whether or not my concrete is cracked? Well, one of the things that I've done is put a lot of work into the documentation on this program. And so if you come down to help here, you can click on help from any one of these dialog boxes, and it's going to pull up full documentation on what you're taking a look at. And so in this case, if I scroll down here to anchor bolt pullout capacity, I can come down and take a look at cracked concrete, and it'll tell me right here, specifying that affects the following strength factors. And here we get some of those sort of obscure psi factors that come out of the code, but you can better understand now how each one of these options is going to affect your design without having to crack open the code, which is the whole goal here. So we are going to say that we have cracked concrete for this one. We are not going to bother welding the anchor bolts to the base plate, but I am going to put some supplemental reinforcement in here to ensure that I have a ductile failure with the seismic. And so here I need to specify what the yield stress is for the rebar that we're going to be putting in, and I'll leave that as a standard 60 KSI. So closing out of that window, the next thing we want to do is go into the loads dialog. And in here I can specify shears and moments and axial forces in both directions. And you'll note sort of we have the sign convention, so I have positive P. I can even specify an uplift, and I could have a separate uplift for my seismic versus my dead or live loads. In this case, we're going to go with 50 kips of dead, 100 kips of live, and 50 kips of axial load for the earthquake. Now, the earthquake is something that can act in both directions, and so we need to bear that in mind, and we need to actually have a reversible load combination set up here. Now, under the shear, I'm going to add 15 kips for that earthquake, and for the moment, I'm going to put in negative 160 kip feet for that as well. So now we've specified these loads. I'm going to close out of there, and now we're into our last window, which is the load combinations. So I come into load combinations, and this is empty right now. Now one thing I can do is click on the LC button up here, and I can actually generate load combinations for all the different codes, whether it's the ACI, aisc, IBC, so on and so forth. In this case, though, I'm just going to enter in a couple of load combinations so that I can get a faster solution so we don't all have to sit around and wait for it, because sometimes that FEA solution with a large number of load combinations can take a little bit of time to run. So I'm going to put in some ACI load combinations here, and under the ACI, I'm allowed to do 1.2 dead, 1 live, and a factor of 1 for my seismic. Now, the important thing is I want to set up another load combination for that. I call that ACI plus. I'm going to call this ACI minus. It's also going to have 1.2 dead and 1 live, but I'm going to put a negative 1 for the seismic load. And what that means is that for this load combination, it's going to take all of these seismic loads that I entered in here and apply them in the reverse direction so that we can check the anchor bolts for both directions, since obviously an earthquake isn't just going to result in forces that are in only one direction. Now, separately, I'm going to take advantage of something, and that is that the aisc has slightly different load combinations than the ACI, and they're going to allow me to use a 0.5 factor for my live load rather than a 1 factor. And so I'll put in aisc plus and minus here, and I'll put that -1 in as well. And so this 0.5 would sort of counteract some of the uplift that's going to be occurring from the seismic. But for the aisc, I only want those load combinations to be considered for the plate design. And similarly, I only want the ACI combinations to be considered for the pullout design, which is why I'm going to check the boxes, as you can see here. So at this point, we've run through all the options, and the last thing to do is just solve. And so I can come up here to this green equal sign, and we're going to run a solution on this. And so you can see it's finished up already, and it's reported our results back to us. And what we can see here is it's picked out a 24-inch by 24-inch base plate. We can see 4 anchor bolts. We can see the plate thickness is 2 1/4 inches. Now on the right, we have our base plate stress and our bearing pressure stress. And you can definitely tell that there was some FEA here. Under the bearing pressure, you can see localized stresses directly underneath the compression flange. And under base plate stress, you can see localized stresses near these anchor bolts where you're starting to get some prying action occurring. But you'll note that the maximum to allowable ratio for both of these is under 1, so we're all set. Now coming down a little farther, the anchor bolts that we chose in this case, they are listed for the aisc checks at the top here. And so here you can see you have your FT, your FV, your FNT, and your FNV, and we're going to combine those using the aisc combinations. And so here you can see your unity checks. So we got about 0.6 and 0.3, and that T means the tension controlled, and that's as opposed to S, which means shear controls, or C, which means that it's a combined tension and shear that actually caused the failure. So let's scroll down a little farther here. This is our anchor bolt pullout capacity results. And so what you can see here is we've got our tension envelope, our shear envelope results. What we're in right now is what's called the analysis and design summary. When you first solve, this pops up, and this is showing you just a summarized worst-case look at the entire situation. Now, if you click on this detail report button up here, what it'll do is actually launch a detail report, and that contains the results for every single load combination and every single anchor bolt in every single direction. So you end up with significantly more data. And it's not necessarily a bad idea if you're going to come in and really check out things in detail to come in here. But for the most part, this sort of summarized report that you get is going to give you enough data to tell what's going on. So let's take a look at what's happening here. We've got a single bolt tension check with a unity of 1.74. And the one thing I always take a look at in here is numbers that jump out at me in red, because those are going to be numbers that fail. So we take a look for the single bolt tension. Here's the different failure modes we mentioned earlier. NSA, that's the steel strength of the anchor bolt. NCB is the cone breakout strength. NPN is the pullout strength. And NSB is the side face blowout. And note that this value is set to 0, and that's because the anchor bolts are far enough away from the edge that side face blowout can't control in this case. And so we also have under seismic, it says SR. Well, that SR means supplemental reinforcement. We did specify earlier that there is to be supplemental reinforcement, and what it's going to do is come back and tell us this is the load that that reinforcement needs to be designed for, and this is the tension reinforcement, and then this is the area of steel that you need to accommodate that load. So I can see that I need 0.573 square inches of supplemental steel on this one in order to meet the seismic requirements. Now, coming down a little farther, here's our shear results, and you can see VSA, shear failure of the bolt. Now, I have all these different VCBs. These are the cone breakouts for the shear forces. That's the sideways cone. I have the VCP, which is the pry out, but all of that passes here. But when I come down here for a single bolt, in this case, load combination 2, bolt number 1, the combined tension and shear is too much for that bolt, so we have a red value here showing us that that would be a failure. Now, for group bolts, we also have a group tension failure here. In this case, it's referring to group T1. And I can find out what group T1 is by going to the detail report. And if I scroll down in here, I get my tension bolt groups listed. So T1 is 1, 2, 3, and 4. So evidently, all 4 bolts are close enough together that they're going to fail in one giant shear cone as opposed to individually. Now, we do check the overall failure as well as the individual failures, and I can tell that since the unity ratio is higher for this individual bolt than for the whole group, that bolt would fail before the entire group did. But, of course, it's one more check that's necessary to do according to the code. And so here we can also see our seismic reinforcement listed. Now, we also have shear grouping going on here, and this is one of the things that ends up becoming very confusing, but what really helps is that we have some bolt group diagrams. So what I can see is that my controlling shear here is group S4, and I can really see just at a glance that a near edge failure of the VCBXX is what's going to control on that one. But what does that even mean? What I can do is I have a button up here that's bolt group diagrams, and when I click on that, this is going to pull up diagrams for each one of the groups, and I can take a look at what the failure modes are. And so if I take a look at group S4, near edge, here's my S4 near edge failure, I can see what it's talking about. It's saying that when a shear occurs in the X direction, that this red area is going to blow out of the concrete, and that it would only take 16.4 kips to do that. Now, granted, I only have 7.5 kips to shear in that direction, so it seems like I'll be all right for this circumstance. But one of the important things about analyzing results is not only being able to read them, but being able to know what to do in order to correct them. So we set this up, and the program solved, and it solved, and we've got these failing results. Well, the reason why it's solved and we're getting failing is because it's not optimizing the anchor bolts. There's far too many parameters to take a look at if you want to just do a straight optimization. Instead, it's optimizing the base plate and then checking the bolts for you afterwards. But it's up to you to determine how you want to correct the base plate in order to get this to work. So the first thing that jumps out at me in terms of seeing a single tension check is that maybe these anchor bolts are just too close to the edge, and it's actually cutting in on the pyramid that is used to resist the pullout for the cone failure. So what I want to do is come back to the base plate dialog, and I'm going to increase the concrete pedestal here to a 42-inch by 42-inch, and I am going to clear the results in order to do that. So now that I've increased that, I can solve again, and it's going to come back, and I can quickly jump down and take a look and see, nope, that really didn't help the situation at all. We're still failing in this case, and so we're going to have to take another step. Well, increasing the depth of the anchor bolts is one thing that I typically always think of, but of course, when we take a look at this situation where we're going to have a group failure and they're all going to pull out at once, it doesn't really matter how deep it is if the entire group is just going to yank out in one shot. So instead of doing that, maybe what we need to do is just spread the load out amongst more bolts. Because I can definitely tell that this bolt number 1 here, it's getting some prying action, and that prying action is causing some additional tension on it that wouldn't otherwise be there. So what I can actually do is come back to my connection here, and I can change this. Instead of 2 bolts per row, I'm going to bump this up to 4 bolts per row. So effectively, I'll be doubling up those bolts in the corners. And so when I solve again now here, what it's going to do is show me what the results would be if I had a total of 8 bolts on this base plate. And with those 8 bolts, we should be able to cut down a lot on the tension per bolt, which is primarily caused by that prying action. And so you can see right here, there's your 8 bolts. And if I scroll down a little farther, nothing's in the red, so at this point we're all set. It looks like my worst case in this case is a unity check of 0.919 for group failure for tension, and that's not really anything to worry about. And here we're at 0.957. So this completely passes, and you'll also note that because of the additional anchor bolts in here and the way things are controlled, that we no longer need any seismic supplemental reinforcing in this case. Now the failure modes have been switched over to ductile, and so it's not a concern any longer. So that's an example of one typical base plate setup. Let's take a look at a little more advanced example to understand some more things about the way this works. Now what I'm actually going to do is open up a file that comes with the RISABase install. There's an examples folder, and in this we have a wide variety of examples that we have full hand calcs for that verify the numbers, and those are actually included with the program. So when I come to example 7 and open this one up, and yeah, that will clear the results. Now I'm in here, and instead of just going through all the dialogue to look at everything, let me just get a solution right now, and that solution is going to show me what this column looks like. Now, something to be aware of with this column setup is we've actually put stiffeners in this case. And so you can see these green stiffeners here. That's specified under connection. And you can see I also have a tube column in this case. So here's my HSS. There's my stiffeners on there in the green. And so those stiffeners are going to cut down a lot on the basically unbraced distance of that base plate. So they're going to cut down a lot on bending and make things a lot more rigid in terms of how the forces are distributed to the anchor bolts. But of course, there's always localized forces due to the stiffeners as well. And if I take a look in here, I can see some of my contours. This is in the detail report for what's happening in some of the localized situations. Now, it also looks to me, by the shape of these contours, that we've got a biaxial load occurring here. And sure enough, looking at the loads, this is a wind load, and we have shears and moments that are occurring in both directions. So here's a setup that works. If I scroll down, nothing's in the red. And the first thing that's going to jump out to me in terms of a realistic design is that those stiffeners are not going to be cheap and not going to be easy to install. So let's do a little value engineering exercise here. I know it's basically a 4-letter word, but it's something that we have to consider more and more often these days. We want to take a look and see whether or not we can remove those stiffeners and still get this base plate to work and end up saving a lot as a result. So let's go to the connection, and we're going to eliminate the stiffen, and we're going to set this one to plain. And we're going to see what the program comes up with for a solution. Now, I pointed out here there's also other methods such as clip angles and channels that you can use to stiffen, as well as just the, you can have a base plate with no anchor bolts whatsoever. All right, so coming back here, you see we've got 3 anchor bolts on each side. That's the way it was specified. It's picked out a 20-inch by 20-inch plate. We've now bumped it up to a 2-inch thickness. And if I scroll down, I'm going to see that I get this group tension failure in terms of unity. And so that's definitely a concern for me. I'm going to have to address that somehow. And so taking a look at this example, let's see what the pedestal looks like. 34 inches by 34 inches. I do have the capability to spread these anchor bolts out a bit. And if I spread them away from each other more, it's possible that I can basically eliminate that group behavior because they'll be too far away from each other to interact with each other. And so what I'm going to do in this case is I'm going to force this base plate to be 24 inches by 24 inches. Now you'll see it's going to solve much faster when I force this size. And when I mention forcing, I just mean that I set the same value for the maximum and minimum. And it does solve a lot faster when you do this because it doesn't have to iterate through every possible size that falls in between. So I'm going to solve this again now. And here's the results. And we can scroll down and take a look. And nope, in this case, that really didn't help. Even spreading them out a little farther really didn't do any good. And so maybe what we can do is we can try increasing the embedment and see if that helps at all. Maybe by increasing the embedment, we can get a little larger cone and a little more resistance from the concrete. And so if I go into the anchor bolts here, right now I have projected length of 4, total length of 14, and I want to get up to a total length of 16. We'll add another 2 inches of embedment and see how this affects things. So now I'll solve again, and we'll take a look. Nope, still failed, really didn't do anything. All right, well, I still have more tricks up my sleeve. I can come back and I can try decreasing the embedment. Now, I know that seems a little counterintuitive, but when you decrease the embedment, you're also decreasing the size of the cone or pyramid around each bolt, and as a result, you're making it less likely that bolt's failure is going to interact with other bolts that are nearby. So maybe we'll try dropping this down to a total AB length of 12 inches so that we only have 8 inches of embedment and see how that works. So let me just solve this again. So I run the solution. Nope, that still didn't do anything. All right, well, let me try one other thing here. I'm going to actually try increasing the base plate size to 28 inches as opposed to 24 inches. So I'm going to enter those values in here. And so now we solve again. So now I have a much larger base plate. And of course, one of the advantages of having this larger base plate is that I'm basically cutting down on the moment arm on the bolts, so I'm eliminating the amount of tension that's occurring on these bolts. But I am also increasing some localized bending in the base plate, and that can actually cause some more prying action or some other issues around there. And so what I find by increasing that base plate size is I've actually made the situation considerably worse. Here you can see now I'm failing in tension and in group tension and in tension and shear combination. So really, after playing around with this, and in preparing for this presentation, I actually played around a lot more with this model, and I found that there was basically nothing you could do in this circumstance to get this to pass. If you add more anchor bolts, it still doesn't do the job because you get the group failure going on. So at the end of the day, we did our due diligence. We took a look at what would happen without stiffeners, but ultimately it looks like we're just going to have to go with a stiffened setup in order to get this to pass. And you can see I still left the base plate size much larger, but if I bump that back down to the original 20 by 20 that we had here, you'll see once again that that passes. So this, as I mentioned, was example number 7 that came out of here, and I just want to show you the references. If I go up to Help here, and under Help Topics, under Design Examples in the contents on the left there, you can see we have these example problems. And if I scroll down under Example 7, if I find that here, you can see these are all of the calculations that show where all the numbers come from on this one. And so you can use this as sort of verification for the program, and this pretty much determines that all these various failure modes and everything has been calculated correctly. So it's a nice thing to have available. So that's the basics of what's going on within the program. Now, one other thing that I wanted to show everyone is we've made this handout available, and let me just access over to that. There's a RISABase quick reference that we've put together, because all those different failure modes that are shown, it can definitely get confusing. And so we have this PDF document. This is a letter-sized document. It's a quick reference guide, and it's something you can keep in your drawer or just keep handy. And so that when you're taking a look at the numbers within RISABase, you can take a look at what the anchor bolt steel is and know that that's VSA. So basically, looking at these bold values, you can quickly tell what type of failure mode the program is talking about here. Now, we also come down and show you the failure and load arrows for the concrete breakouts for group failure. And so here's your VCB-ZZ, ZX, XZ, and XX. And the way this works basically is that the capital letter is the failure direction, and the capital letter is the failure mode, and lowercase letter is the failure direction. You can see I even get mixed up with this, and I use it so much. That's why I put together that sheet, and that's actually going to be available on the website after the presentation is over. So it's a handy reference there, and I'm just going to come back in here real quick to take a look at some of the details and make sure that we didn't miss anything in here. So I mentioned that we have the aisc checks on there, and this is where you can actually get all your bolt forces as well if you want to take a look at those. Those fall under the tension. Here's all the anchor bolt pullout results, and this is under the detailed report as opposed to the basic analysis summary.